In this video, we're going to look at one of my favorite statistical tests, the chi-square test. And we'll do it in a way that anyone can understand. We'll start off with what it actually is and then work through an example so you know when to use it and how to interpret it. Let's get into it. The chi-square test is used to determine if there is a significant association between two categorical variables. Categorical meaning that they are made up of groups or categories rather than continuous values like height or weight. You can also think of them as qualitative data. So for example, eye color is a categorical variable because it's made up of different categories like blue eyes, brown eyes, green eyes, etc. The same goes for gender. It's a categorical variable made up of the categories male and female. There are different types of chi-square tests. However, in this video, we're going to focus on the chi-square test of independence, which looks at whether two categorical variables are independent of each other. That is, does the presence or absence of one variable have any influence on the presence or absence of the other? If we go back to our eye color example, we might hypothesize that eye color is independent of gender. In other words, the proportion of males with blue eyes is the same as the proportion of females with blue eyes. Later in this video, we'll see how to test this hypothesis. To conduct a chi-square test of independence, we need to follow these 4 steps. Step 1. State the hypotheses. Remember, the null hypothesis is always about the population, and in this case, it's that the variables are independent. How is the alternative hypothesis? And it states that the variables are not independent. Step 2. Find the expected frequencies. Step 3. Calculate the chi-square test statistic. And Step 4. Make a decision. This will involve finding the p-value and comparing it to a significance level. Let's now work through an example to show you how this works. Imagine that we want to investigate if there is an association between smoking status and whether someone gets lung cancer. Here, smoking status is our first categorical variable and it has 2 categories, smoker and non-smoker. Lung cancer is our second categorical variable and it also has 2 categories, yes and no. We can represent this data in a two-way frequency table called a contingency table. Now notice that the top of the table represents the rows and the side of the table represents the columns. Each cell of the table represents the frequency of an outcome for both variables together. For example, the cell in the first row and first column represents the number of smokers who also have lung cancer. We could also describe this as the number of people in the sample who both smoke and have lung cancer. Similarly, the cell in the second row and second column represents the number of non-smokers who do not have lung cancer. We've already stated the null hypothesis in Step 1. Now let us move on to Step 2 and find the expected frequencies. The expected frequency for each cell represents the frequency we would expect to see if the variables were independent. To calculate the expected frequency, we multiply the row total by the column total and divide by the overall sample size. So for example, the expected frequency for the first row and first column would be calculated as follows. The row total is 80 plus 20 equals 100, and the column total is 60 plus 20 equals 80. So the expected frequency for the first row and first column would be 100 times 80 divided by 100 equals 80. You can think of this as the proportion of smokers in the sample, 80%, times the proportion of people with lung cancer in the sample, 60%, which equals 48%. Or you can just memorize the formula if you like. You would do the same calculation for all the other cells. Now let's move on to Step 3 and calculate the chi-square test statistic. To do this, we take the difference between the observed frequency and the expected frequency for each cell, square it, and then divide by the expected frequency. Then we add up all the results. So looking at the first cell, the chi-square contribution for that cell would be the difference between 60 and 80 squared. So 400 divided by 80 equals 5. We would do the same calculation for all the other cells and then add up the results to get our chi-square test statistic. Once you've done all the calculations, you should get a chi-square test statistic of 10. Now remember that the larger the chi-square test statistic, the worse it is. Why? Well, it means that the observed frequencies are very different from the expected frequencies. And that can only happen if the variables are not independent. So if the chi-square test statistic is really large, we can reject the null hypothesis and conclude that the variables are not independent. But if the chi-square test statistic is small, it means that the observed frequencies are similar to the expected frequencies, which supports the idea that the variables are independent. But how do we decide if the chi-square test statistic is large or small? Well, we compare it to a critical value from the chi-square distribution. To do this, we need to know the degrees of freedom, which is calculated as the product of the number of rows minus 1 and the number of columns minus 1. In this case, the degrees of freedom would be 1. Then we need to choose a significance level. The most commonly used significance levels are 0.05 and 0. Let's now assume that we looked up the critical value and found it to be 3.8 for 1. This means that if our chi-square test statistic is greater than 3.8 for 1, we would reject the null hypothesis. Since our chi-square test statistic of 10 is greater than the critical value of 3.8 for 1, we reject the null hypothesis and conclude that there is a significant association between smoking status and lung cancer. In other words, smoking status and lung cancer are not independent. In fact, we can say that lung cancer is associated with smokers. Finally, step 4, make a decision. We've already done this since we compared the chi-square test statistic to the critical value. However, another way to make a decision is to find the p-value and compare it to the significance level. The p-value represents the probability of obtaining the observed results, or more extreme if the null hypothesis is true. If the p-value is less than the significance level, we reject the null hypothesis. In this case, you would get a p-value of 0.01, which is less than our significance level of 0.05. Therefore, we would still reject the null hypothesis. Now, I didn't actually calculate the p-value or the degrees of freedom by hand. Instead, I used a chi-square calculator, which you can find in the description below. If you want to learn more about the chi-square test, check out the video link in the description below. Thanks for watching and see you next time.